Swayam Prabha. Digital India. Educated India.
Thank you very much. And thank you for the invitation to give this lecture. My apologies that I could not come to present in person. I think you can see my slides and you can hear me, so yes. I will go on.
Yeah, we can hear you and see,
see the slides. I'm just
also
trying to get, okay. So my talk is divided into 5 parts, and I will start with the introduction. On that, we have a lot of resources, and these resources are not uniformly distributed, but we need to convert these resources to the products that we need, that you see on the right-hand side, for our own sustainability on Earth. And so the major issues from a product point of view is what to make, how to make, sustainability issues, safety, health, environmental impacts issues, and many more. So we will see how we can do this. From the figure on the left-hand side, it is clear that product development is inseparable from process development of a successful realization of a product. Let me also define what I mean by design is a synthesis activity. Development includes management of all activities in the development process, from conceptualization of ideas to their realization. Product design refers to the design activities related to defining the product, that is what to make. Process design refers to design activities related to designing the process for manufacturing a specified product, how to make. With that definition, I will try to show briefly what is the connection between the process design and product design. As we know very well, in process design, we take raw materials, we convert to product. That is the product we need. And in order to do that, we have to design the process flow sheet, including the operating conditions and then equipment parameters. We can look at the product design problem. Similarly, we have atoms and molecules, or molecules that we need to combine together to form a product whose properties should be the properties that the process is making. But the product also has functions that needs to be matched, and we manipulate the molecules and mixtures to get that product that we need. So what is the connection? The process needs to make a product with the properties that have been designed. Normally we stop at that, but actually there is another process that also needs to be considered. That is, does the product have the functions that were designed? And that is dependent on the application of the product. So we need the application process where we have a product, we evaluate the performance, and we need to combine and see whether the performance that was the product functions that were designed is matched with the performance. So when we integrate process and product, we need to integrate and look at both these issues. Excuse me, I have a cough problem. So one can see that there are 2 kinds of process connection. One is a manufacturing process, another is application process. In some cases, we do not look at the manufacturing process. In some cases, we do not look at the application process. But both are important and needs to be looked at. General overview of the product development stages. We start with the market study. If you want to go ahead, we do the preliminary product design. Then we do the preliminary conceptual process design. If they are found to be feasible, we do the prototyping. If we want to go forward, then we do the detailed feasibility study, process design, economic analysis. and then finally engineering, design, plan, scale up before product launch. Of course, I'm not showing all the stages, just highlighting those stages where PSE, process systems engineering, could be involved. Also, one should note that each of those stages that are shown in the figure, there are different algorithms within it, and they are at different scales also. For example, the product design could be computer-aided molecular design or mixture design, or even based on simulation and or experiment and many things. Depending on how these stages are performed, time and cost to market would influence the early decisions, and we have to look at the sustainable development issues. So from a point of view of this product development stages, they actually depend on which type of product. So what you see on the example on the right is from the petrochemical industry. There is a part which is extraction of the oil. There is a part which is using the oil. So one could say upstream, downstream. One could also say business to business, because we are getting the oil, we are producing chemicals, but it's not for consumers. If we look at another example, that is from a petrochemical industry, or pharma industry, there it is business to consumer, and the stages are different and the time scales are different. So I'm just showing two examples. If we take different examples, we will see basically most of the stages are in the same sequence that is shown on the figure on the left. But the time scale and the details of them are different. So that is one thing that needs to be considered when we are talking about product design and development. So with this introduction, I will move on to problem definition and examples. Many of the things that I'm going to show have been reported by these two special issues on chemical product design that I actually guest edited for the journal. And the keywords there were quantum computing, AI-based computer-aided molecular design, hybrid ML-based techniques, material design, and many more. I will not highlight these. I will request you to see these papers in the journals, but I will give you my overview of them. What the figure shows is, on one side is product synthesis on the left, and you see different examples of product, and on the right, process synthesis, and you see different examples of the stages. That is unit operation, a more detailed unit operation, collection of unit operations in the flow sheet. Common to both of them, right in the middle, is a set of physical-chemical properties, because we are dealing with chemicals. We are not talking about any products. We are talking about chemicals-based products, and chemicals have a set of physical-chemical properties that are common to both the product and the process. And then there are some properties that define the process function, and then there are some properties that define the product function. So one important element of any chemicals-based product design as well as development are data of the properties, but data is not available for all the properties and all the chemicals, so we need models. A challenge and opportunity here is reliable data models of wide application range. Whatever means one can use, and of course there are lots of means to do that. Here to highlight again the importance of definition of the problem, we have classified the products into different classes like single species, multiple species, devices. And then under single species, there are small or there is large, multiple species, formulated, functional, and then devices. What is important is if you look at the green arrows, and let's take just one of them, the key factors of design. If it is small molecules, cost of production is very important. Product performance is very important. That is more related to commodity chemicals. If you look at the multiple species products, functional or formulated, the product function is very important. First time correct is very important. Time to market is very important. If you look at the challenges in design, one can see different kinds of challenges. In the case of small, it's translation of needs to molecular structure. If you look at the formulated or functional, delivering product functions defined by the needs. So how do we understand, first of all, which product we need, what properties or functions this product would have, and how do we translate the functions into properties and their constraint values or target values. These are very, very important. At the bottom, I would like to emphasize again, these days, environmental impact and sustainability is a must. They also need to be looked at. Let me show just some brief examples of the product design problem definition. We need to understand how the product design problem can be defined correctly. So here is an example of, we are looking for a solvent that will extract the real product that we want of a chemical process. But what should be this solvent? The solvent should be able to separate A from B, let's say, and A, B forms azeotrope. So B is the product we want to get. So what the solvent should do is to be able to have distillation boundary as high as possible and should extract B with the least amount of solvent needed. So I'm just showing you the operating line. So the higher the dashed curve that you see is, the less solvent would be needed. And if the dashed curve then touches the binary of solute B with solvent, then we don't need to worry about A. So the separation of B and the solvent would be very easy. So if we know already that this is the curve we want, we can figure out all the properties that would be needed, and then we can try to go to computer-aided molecular design and say, can we find this solvent? So definition of the problem, therefore, is very important to be able to find the solvent we need. And I'm not showing here the environmental impacts and other things. We will see them later. Another problem typical in pharmaceutical industry is crystallization or extraction of the product from the reaction effluent and then further purifying. So usually one can do cooling crystallization. That is, you cool the mixture, you take the solid out, the solid product. But if you cannot cool further, then one has to do something else. So again, what are the properties that are needed? I'm giving you a list of properties on the left-hand side. What we need to do if we want to do cooling crystallization followed by drowning out crystallization is that we first find a solvent that will give us enough of the solute. Then we cannot reduce the temperature further. So what we do is we put an anti-solvent, which is totally miscible with the solvent and which shifts the saturation curve so that at the same temperature we get more. And so the values that I've written on with the green number, first is given for the solute, for the solvent, and then afterwards is given for the anti-solvent. And the important thing here is the solvent and the anti-solvent must be totally miscible. So how to specify the desired phase diagram here? which is the product of interest, how to include the process model, because we need a crystallization model here. How to include all of these is a challenge. And we have the opportunity for process systems engineering. Another one is tailor-made blends or fuels. That means we have let's say a gasoline. Can we add some extra compounds in it so that it will have the desired special properties of gasoline? Maybe it will run the engine longer, consumption will be less, and therefore environmental impact will be less. So these kind of problems can be solved. Again, what are the target properties of the gasoline that we have to specify? Can we measure them? Can we calculate them? And then how to find the blend is a mixed integer optimization, nonlinear optimization problem depending on the property models. So like this, we can solve liquid fuels, solvent blends, lubricants, and many more. An interesting product is formulations, and I'm talking about liquid formulations. Then what is the purpose of the product? Here is an insect repellent to be effective against mosquitoes. The performance should be long-lasting, low toxicity, water-based formula, and so on. We need to convert them into target properties. So long-lasting, low toxicity, these are related to evaporation rate, the LC50 value, and so on. And then once we know that these are the target properties, we need to provide upper and lower bounds so that when we are trying to find the optimal recipe for the product, we can match these values. And then you can see that there are some properties like pleasant smell, good skin feeling. We don't know which properties they are yet, but we need to do experiments to check them. I will skip this for time, but this is an interesting problem that still we are struggling to find out how to model and solve with computers the design of a soap bar, like the Dove soap bar. And also refrigerant, they are very good, but they cause environmental problems, especially global warming and ozone depletion. And R134A is a very commonly used refrigerant that is being phased out. So what would be an ideal refrigerant or a refrigerant blend that will have exactly the cycle operation that we would want, but does not have the problems of global warming potential or ozone depletion or flammability or dangerous production operation? That is still a problem that people are working on. Here is I'm not sure if you can see this figure, but what I'm trying to show here is how to manage the complexity. So on the top green part on the right, this is the problem definition, and it's just showing some of the paths to different problem definition. So problem can be, as we said, single species, multiple species devices. Under single species is small, large, so they generate different paths. Once the problem is defined, then in the center is the main interface that connects the problem to the ways to solve the problem. Then based on the problem, one needs to know what kind of candidates are we interested in. Is it single species, multiple species? Are these organic molecules, inorganic molecules? All of these are needed to find out what kind of candidates. Then what kind of properties? And then based on the candidates and the properties, we need to go to the database. We need to go to the property library. So the property library then has a classification of knowledge of different kinds of property models that are needed for different properties. And then for each type of model, what are the different paths to them? Pure compound property, mixture property, phase equilibrium property, and so on. So this is the complex structure of computer-aided chemical product design. If we want to develop a framework for computer-aided product design, that's the structure the PSE community needs to resolve and find out in which of these steps machine learning, for example, could be used, in which of these steps AI-based techniques could be used, and so on. With that, I go to the next part, which is problem solution strategies and tools. Very simply, as we talked about, if we want to develop a product or find a product based on the definition we have given, we need building blocks to generate the molecule or candidate. So the candidate building blocks could be atoms, which can be combined to form functional groups, which can be combined to form compounds. And here are some examples of compounds. Once we have the compound, we need the property models or data to calculate the property. So just having the data is not enough because there's very little chance that a molecule we would generate would have its data. So predictive model for properties is very important. An example of, if we know that there is a molecule that serves a purpose, for example, benzene is a good solvent, but we cannot use it because of its carcinogenic properties. So how can we replace benzene? Then we find out that we take building blocks that do not form aromatic compounds. So we avoid having problems like of benzene. Then we know the target properties of benzene, the solvent properties, which are very good. So we combine the groups to form molecules, and then we check the properties. And if they are satisfied, we generate more molecules through isomer generation. And then finally, we check whether they satisfied our requirement. This is the generate and test. We can automate that by putting it into a mixed integer linear or nonlinear programming algorithm. And so we will do basically the same thing, but we will not do generate and test. If you remember the stages of product development, there were different stages. For each stage, if we had a model, then we could develop everything on a model-based system. So here are the models for the product, the process, and the property. Here is the formulation of the problem as a mixed integer linear, nonlinear programming. Here are all the models for quality assurance, for economics, for performance evaluation, sustainability, environmental impact, all of that. We put them as constraints, and then we solve the problem and we get the solution. So that's how a structure that I showed before could be handled through this kind of models. Are there models like that? Yes, there are publications that have reported models of all of these and solved in a simple way some of the product design problems. Let me skip this in the interest of time. I'm just showing that all those equations can be structured in a very nice way, structured way, and then there are different ways to solve those problems. And then I will advertise a little bit our computer-aided product design software. In the middle is the interface which allows user to solve single species problems, multiple species problems, formulations, devices, and so on. To do this, these are the 4 types of problems it would solve. To do this, we need databases, we need property models, we need solution methods and algorithms, and we need product function evaluation routines. So like evaporation rate and so on. And then the database needs to be a wide range of databases, not just chemical properties, but a lot of different databases. Property models, we need a wide range of property models. Methods, we need generate and test, we need optimization methods, we need specific methods for refrigerant, for solvents, and so on. And then on the right-hand side, you see evaporation rate, phase stability, friction factor. These are specific product function related, performance related calculations that also need to be done when experiments also can be done. So that's the APD, and this has been now incorporated into a more general product design problem, and it's very complex here, but I've highlighted in two sections. First are the stages. Steps 1 to 4 are define the problem. Steps 5 and 6 is design analysis. Step 7 is verification. So I will just highlight the design analysis part. So these are not all the tools, it's just for the design analysis for some kind of problems. We have the product design model, for example, molecular design. We can do that. Then below you see product design template. So in many cases, the product design would follow the same steps, but the properties would be different, the models would be different, and so on. So in order for the user to define their problem, we have a product design template. Then we need the property and a wide range of property models. Then we need, if we need to develop new models, we need a model development tool. And then, as I said, we need some special tools. For example, refrigerants. We need a special tool for refrigerants because they are small molecules and the property models that we have are not actually valid for the small molecules. So this is also a warning for those who are using even our models for property prediction. For larger molecules, do not use that for refrigerant because they will not give the right result. Also, I will highlight the chemical substitution problem a little bit later because that is becoming more and more important. So some new features that we have added is wider application range of property prediction. ProRefD is for refrigerant design and chemical substitution and analysis. If you remember the crystallization example, here is the solution for it. First, we find the solvent. The solvent is the one that takes the curve to the left, the purple curve. So the original curve is black, which is on the right. So better solubility means it goes to the left. Then at the same temperature, we want more solvent to be solute to be crystallized out. So in this case, again, if we take now the black curve as the original, we want to move it to the left to get more solutes crystallized out. So we can do that also. I will go to the chemical analysis and substitution. Why is this important? Because nearly 95% of all manufactured goods in some form use industrial chemicals. Nearly 500,000, I think it's more than more closer to 1 million chemicals have been registered and used. Out of this, 40 to 60,000 we can see in different products, identify them, and only 20,000 have actual measured data, quantitative data. There is a lot of qualitative data, but actual quantitative measured data is only around 20,000. So we need to identify the contaminants, the harmful chemicals, and substitute them before they cause problems. So we have developed an algorithm where the user gives the chemicals they have, whether it's in a process or in a product. We take these chemicals, we go to different databases and find out what their properties are and flag them if they have any problem with physical hazards or environmental hazards or equipment hazards and so on. And then if they are flagged, we find alternative to the product design algorithms. And then once everything is satisfied, we give a report together with the sustainability report, the LCA, and so on. Why this is important? We can see that. But first, to just highlight that we have those databases, and there is a lot of, we have collected nearly 900,000 chemicals with qualitative data at least. And we have models to fill out the gap. So here is a very simple example, the insect repellent that I talked about. If you look in the market, most of the products have DEET as the active ingredient. So the function of DEET is to keep the mosquitoes away. But if we look at the hazards, DEET has quite a lot of health hazards and environmental hazards. So can we replace DEET with something else? We look in the literature, we find out that picaridin can also be used as active ingredient, and it does not have the same strong health hazards and environmental hazards as DEET. And so in fact, this is quite a good replacement for DEET. If any of you want to make insect repellent, forget about DEET and use picaridin. This one, again, I'm sure you cannot see it, but this example is coming from CO2 capture. Let's say CO2 is in a shell gas kind of model shell gas mixture, and we need to remove the CO2. So there is CO2, there is methane, ethane, hydrogen, and so on. The last compound is the solvent, diethanolamine. So the physical properties are given, and now the hazardous properties are given. So red is danger, and yellow is warning. So if we look at this, the solvent actually has the most danger and warnings. CO2 on the left has only 2 warnings, that it is a high pressure, the gas is used under high pressure. But if we look at methane, ethane, propane, they have much more danger. So we have to be sure that when we are capturing CO2, there is no leakage of methane, ethane, hydrogen. When we are operating this process, we have to make sure that the human is not affected by the solvent. Remember the solvent-based extraction that we talked about? The ideal separation would be obtained by hexanal, and hexanal does not have any warning or danger mark in the hazardous analysis. All the others have. So again, we can very quickly find out, once we have found the alternatives, that they do not have any problems with respect to safety, health, and hazards. This is the software. I will just skip that. And an advertisement that most of the information can be found on the internet. Finally, conclusions. And I know that both Rex and Marianthi has mentioned these things, but in a separate way, I'm just also showing that the current challenges we are facing on Earth require new definitions of the scope and significance of product process development, adding to the complexity of the problems being solved. But we have the tools and means to do it, and the community is very active. Types of products and their associated manufacturing processes differ with respect to different industrial sectors. Therefore, computer-aided methods and tools need to be flexible, adaptable, so that a wide range of problems can be solved. Concepts, I hope people will agree with me. Concepts of digitalization, machine learning, data analysis, AI, for me are not new, but renewed interest in their use is a positive development, and we need to make sure that they are used in the correct and appropriate way. Reduction of time and cost to market is not sufficient. Issues related to sustainability, safety, hazards, environment, etc., also need to be considered, especially after the end of the pandemic or hopefully the end of the pandemic. Very much. I will be happy to take questions.
Thank you, Professor Gani, for that very fascinating and systematic look at product design. And we have about 5 minutes for questions. I think he has summarized his life journey, if I'm not wrong. He's been at it for the last 34, 40 years, and you can see the outcome of that.
I'm Anwar from Institute of Engineers, Malaysia. So, Dr. Rafiq, thank you very much for your presentation, mainly on this chemical product. So, my question or concern on this chemical product, just want to have some understanding about the development of this chemical product, whereby what I can see is that to develop totally new product, where we have issues and operating platforms or plants, right? So we try to mitigate from the problem statement. On top of that, we try to come up with a similar product that we have used or we are using currently in order to mitigate mainly from upstream industry in terms of hydrate issues, all those stuff. So my question is that just now you were highlighting about mainly about hazardous safety, all those stuff, and not really much on the cost. Even you at the last point during on the conclusion slide that you highlighted that of course it is not really on reducing the time and cost, but more importantly on the safety, all the stuff. But from
Question short, please. I mean, so
yeah. So particularly is that in industry, ultimately, if we are following the policy, as long we don't have any policy or regulation, all right. So we not really keen to go for any new product to replace on existing chemicals that to be used to mitigate all these issues. So how do you think that in order to further enhance, come up with new products to consider all these life cycle costs, so that the new product is really can be used or can be proposed to replace existing chemicals that already in place? Thank you.
I think if I can break up your question into different parts, and I will be short. The first is to make a correction here. I'm not saying that time to market and cost to market are not important. They are very important. And if the cost economics is infeasible, the product will never go to market. So what I'm saying is that time and cost are important and they have to be satisfied, but at the same time, the other issues also need to be satisfied, because we cannot market a product and say, okay, this is very good, let's say a very good shampoo, but there could be other effects that we did not look at. So then the question of new innovative products is actually, we are not talking about totally new chemical or totally new product. Most of these problems are, we have an existing product. That's why the market study is very important. What are the problems with that product? Can that product be significantly improved by maybe substituting one chemical with another chemical? And that is very common, actually. If one looks at the competition between different product developers, you will see that they are very secretive about their recipe, because it's one small chemical that can make a difference. So identifying the needs, defining the needs in terms of properties, and then whether by luck or by actual work, one can find the chemical that can make the replacement and can be a successful product. So all of these can be done, but I think process systems engineering can help to make those decisions faster and better.
There is one question from an online thing. Please, can you please read it out?
Yeah, I
The
will.
name of the person who was asked.
I will read it out. There's a question from Saripali Subhadra Devi. She's asking how we can incorporate the mechanism aspects in the process design model. If we change solvent, catalyst, etc., the mechanism may vary and we get the different undesired products.
It's a very valid question, but again, that's why I emphasized a little bit more on the definition of the problem. If we are talking about, let's say, solvent replacement, the solvent is used for, let's say, extractive distillation. So we are not changing the extractive distillation process. What we are changing is only the solvent. And in some cases, that solvent could be found without even changing the distillation column. So all those can be kept as they are, but a new solvent would provide better operation and safer operation. With the reactions, it's a little bit more difficult. And I agree that catalyst design is much more complicated, but people are working, developing computer-aided techniques for catalyst design. There, it is very important to be able to stop the bioreactor. So that's a challenge. I'm not into material design. Those property modeling is more difficult. So, but this is a problem that I think the catalyst design people should be able to look at and solve.
Thank you, Professor Gani, for those answering those questions. And since we are about 5 minutes over the board, and I think dinner is probably being also waiting for you, or vice versa. So we will conclude the thing. And I would like to thank all the speakers who have today inaugurated this symposium in such a grand manner. And also, I'd like to thank the organizers for giving me the opportunity to share this session. Thank you.